Hello everyone. Today we're going to be talking about the principles and applications of UV-vis spectroscopy and more specifically fluorescence. So first, let's talk about what exactly is UV-vis spectroscopy. So UV-vis spectroscopy is a technique that examines how molecules interact with light in the UV visible region of the electromagnetic spectrum, which is around 200 to 800 nanometers. And as seen in that figure in the top right, when the energy of an absorbed photon matches the energy gap between the ground state and the excited electronic state, an electron can be promoted to that excited electronic state. Energy is absorbed by a molecule, an electron from the HOMO is promoted to the excited singlet state. And at this point, a couple different paths can be taken. So, as seen in the top right figure, when an electron is promoted to the excited singlet state, it can then undergo a couple of non-radiative vibrational relaxations down to the ground vibrational level of the excited singlet state. At this point, the electron can then relax down to the ground state and emit light in a process that we know as fluorescence. So when a photon undergoes this emission at excitation, it's typically at a longer wavelength, and this is known as the Stokes shift. And this is due to the equation in the bottom right, E equals hc over lambda. So we can kind of quantify the energy of these emissions by the length of the arrow in the top right figure. The absorption arrow is longer than the fluorescence arrow, and due to that, the fluorescence arrow is going to be a lower energy. And as we see in the equation in the bottom right, energy and the wavelength of light are inversely proportionate. So if the energy is smaller, the wavelength is going to be larger, which leads to a slight redshift of your light. And due to the slight redshifting of the photon emitted when the molecule fluoresces, the emission spectrum of a molecule will be a mirror image of the absorbance spectrum. To further illustrate that last point, we can look at this absorbance and emission spectra of this chemical DCJTB. So on the left side, we have the absorbance spectra, and on the right side, we have the emission spectrum. So as we can kind of see, right around 500 nanometers, the absorbance spectra peaks out. At the same time, you start to see a rise in our emission spectra. And it's almost like it's mirrored roughly around the 560 nanometer range.
I'll be comparing fluorescence and phosphorescence. To begin, we'll be taking a look at the Jablonski diagram here on the right. Both processes start the same way. This being a molecule in its ground singlet state absorbs a photon and is then promoted to an excited singlet state as 1. This absorption step is extremely fast to keep in mind. Now, where these two begin to differ is for fluorescence, the electron relaxes a little vibrationally and then drops straight back down from S1 to S0, the ground state, emitting a photon. This radioactive decay happens in the nanosecond timescale. Because some energy is lost as heat first, the emitted light has a longer wavelength than the absorbed light. This is known as Stokes shift, as mentioned before. Now, in phosphorescence, the excited electron state first crosses over to the triplet state T1, then returns straight back down to the ground state S0. The return from T1 to a single ground state is spin forbidden. Now, this doesn't mean that the transition won't happen. It just means that the transition between a triplet and a singlet state violates spin selection rules, so it is strongly suppressed, therefore happens slowly. This is why for phosphorescent glow-in-the-dark materials, they keep glowing even after the light source is removed. Whereas for things for like fluorescent materials, they almost stop immediately.
Fluorophores are fluorescent molecules that usually contain aromatic or conjugated systems. These structures allow electrons to delocalize and move between energy levels, which is what makes fluorescence possible. Some common examples of phosphors include fluorescein and GFP, which is green fluorescent protein, which naturally glows green because of its structure. Two important properties that we use to describe fluorescence are quantum yield and fluorescence lifetime. Quantum yield tells us how efficiently the molecule re-emits absorbed photons, and fluorescence lifetime tells us how long the molecule stays in the excited state before emitting light. Fluorescence can be measured using fluorescent spectroscopy or fluorescence microscopy, where the emitted light is separated from the excitation light so the fluorescent signal can be seen clearly. On the right is an integration sphere setup, which is one way to measure quantum yield. It collects all the emitted photons so we can compare the number of photons emitted to the number of absorbed.
Hi, my name is Enrique, and I'll be going over some real-world applications of UV-vis spectroscopy. So our first application is in the pharmaceutical industry, where there's a technique called UV hyperspectral imaging. In regular UV-vis, we usually just get one absorbance spectrum for an entire sample, but in the hyperspectral imaging technique, we get a full UV spectrum at every single pixel in an image, which means you can actually map out the entire chemical composition of something like a tablet. In a 2021 study by Aktash and colleagues, this method was able to distinguish 3 different active pharmaceutical ingredients by only using their unique absorption peaks. Monitoring their electronic transitions allowed us to see the clear difference in hyperspectral data, which connected the molecular structure directly to what we see in the spectrum. Another application is the UV-vis is used in environmental monitoring, especially in water treatment plants. Many modern facilities use only UV-vis sensors that constantly measure the absorption of flowing water in real time. Pollutants such as nitrates and nitrites can be monitored fairly easily to see how polluted an environment is. So overall, UV-vis spectroscopy reveals electronic transitions in molecules, while fluorescence provides insight into how excited states relax. These techniques bridge quantum mechanics and real-world chemical analysis, which allows scientists to identify compounds, study their structures, and monitor environmental and industrial processes. Altogether, UV-vis and fluorescence remain essential tools across chemistry, biology, and environmental sciences industry. Here is our references slide, and have a good day.